Hello there, WINDPOWER students. Dr. Shragi here. I apologize. I have a little bit of an allergy or a cold or something today, and my voice is a little bit raspy, but I think we'll get through this lecture today, which is part of Chapter 3 in the Landberg textbook. It's a section of the book that was labeled, What Do We Measure? And when you just look through the table of contents of the book, it might not have been clear what we're talking about here. You might have gotten the idea that this is going to be like what happens at a weather station. Oh, we measure temperature and humidity and pressure and so on. But that's not actually what we're going for here. What we mean in this section here is, what do the instruments actually tell us? What is this number? What does it reflect? What is it representative of? So, like look at the top of the screen here and you can see this wind farm that we're supposedly going to be building on some site. And let's say that you are coming onto this project and somebody's already been operating some kind of meteorological stations at that site, and they gladly email you the file that contains the observations. And now this little screen that I have here is actually the top of the file. You might have noticed that some of the places in the textbook, there's actually, it refers back to a file you can download from the author's website for some of the problems and so on. To be honest, I haven't decided yet if I'm going to have you guys do any of those problems, but this is the set of that's what the file looks like, and it goes on for like 1,000,000 lines of data. And on each line refers in this case to one observation that the instrument was taking. Well, you first start off with this giant number that, depending on how much experience you have working with observations, you would already suspect is the timestamp that records when this observation was taken. In this case, it is the 2001 means it was 2001, 01 means January, the day is 01, and the hour is 00, and the minute was 05. In general, there are some kind of format like that. There would always be documentation that explained what that format was, but that's just what it is in this particular case. And a format like that is easy to read in a computer program or Excel, like that you wrote, or something like Excel. So this timestamp here, the timestamp is not terribly tricky. Then there's, in this case, two more values that are comma separated. And in this particular case of this file that they use in the textbook, the first number is the wind speed in meters per second, and the second number is the direction of the wind, and we'll describe at a later point how we quantify the direction of the wind like that. But the central question I want to ask in this lecture is, what does it mean when the file is telling us that the wind speed was 7.42 meters per second at 5 minutes after midnight on January 1st? What is that? When the file says that, what does that mean about what was happening at that location at that time that the sensor measured? Well, let's actually figure out what that would mean. Now, as we're going to see in a later lecture in this module, there's actually lots of technologies that can be used to measure wind speed. And each of them produces some kind of signal with a piece of electronic equipment that can then be measured and converted into some kind of information about what was going on in the atmosphere at this time. Let's just take the obvious example of, like, if this was a wind measurement and it was taken by the little cup anemometer, the little spinning cups that spin in the wind and so on. In the case of a cup anemometer, we'll learn more about them in a coming lecture, but the basic way they work is the shaft that is spinning actually drives a small generator, and that small generator produces a voltage on a line, which then there are standard pieces of equipment that can measure the strength of that voltage. Excuse me. Now, there's a lot of ways in which this could go wrong. I mean, just because there's a certain amount of voltage on the line doesn't necessarily mean you have great information yet about what the wind is doing. For example, wind speeds can change in fractions of a second. Does a change in the speed of the wind result in an instantaneous change on the voltage produced by that generator, or is there some kind of lag? Does it take time to spin up the generator? Does it take time for that generator to elevate the voltage on the line, for the equipment that's measuring the voltage to determine that the voltage has gone up? What is the lag here? Another point is, do other factors other than the wind speed produce changes in the voltage produced by the generator? For example, maybe at the same wind speed, the amount of voltage being produced depends on things like the temperature. Would have to know that from the documentation that came with your cup anemometer, and you'd have to know how to correct for that. How small of a change in the wind and thus in the change in the voltage on the generator can you actually measure with your equipment? That would of course be another way of saying the resolution of your data, just to throw back to an earlier lecture. Okay, so if the wind speed picks up by 1/10 of a meter per second, does that produce a large enough change in voltage coming off of the generator for you to actually measure it? For that matter, how precise are these measurements? How precisely can you determine, like how many significant digits can you determine the speed of the wind? And for that matter, how accurate is the relationship between the wind speed and how much voltage is being thrown on that generator that you are measuring? That might depend on a lot of different things about how accurate those, over what range of wind speeds, for example, that anemometer is designed to be working, or over what range of temperatures and so on, how well it's maintained and so on. So there's a lot of questions right off the bat. Just because you have this voltage that's being produced by this generator does not necessarily mean you have, unequivocal knowledge of what the wind was doing. But at some point, whatever you have decided this means, whatever your algorithm has decided this means, this much voltage is on that line, therefore we're going to assign that is equivalent to a wind speed of 7.42 meters per second. At some point then a piece of equipment on the line called a data logger will actually record that into a file. Okay. Sometimes the data logger is actually where you have encoded your algorithms, that is what's doing this. Sometimes it's part of the equipment itself. We'll see examples of both of those. But either way, at some point the data logger is what's actually doing the heavy lifting here of converting this into some kind of file and writing it to something like a little SD card or a flash drive or something like that, or maybe transmitting it over some kind of network to where you're reading it or whatever. Typically if they're not being used for like operational, if you're just trying to gather data, it's typically writing it to some kind of very efficient like SD card or USB drive, just because that's very efficient and doesn't take a lot of power the way like powering antennas do and stuff like that. So okay, we've gotten the data logger to write a file that told us that at 5 minutes after midnight on January 1st, the wind speed was 7.42 meters per second. That still doesn't actually tell us what the atmosphere was doing. We see now how we got that number. But what does that mean? What was moving 7.42 meters per second? I mean, does that mean that at 5 minutes after midnight on January 1st, the wind speed was whatever to produce that much voltage right at that exact second? Literally as the second hand hit 5 minutes after midnight, that was the voltage on the line and it corresponded to 7.42 meters per second? Probably not. In general, that is not the way it works. Because wind is so variable. From second to second and from fraction of second to fraction of second, there's a lot of variability to the winds, especially during the day. And that can be really hard to even visualize. Picture like you're up on a high, like a fire tower or something like that, or up on a high pole looking down on a field of wheat. And you can see how the wheat is blowing in the wind, and as you watch closely, you'd be able to see how there's places where there's gusts going on, and there's swirls, like dust devils and eddies and such in the flow going on any given time. If you were just recording the wind speed at one location in that field, you'd see that in fact the wind speed goes up and down quite a lot, even on the scale of seconds. I mean, there are surprisingly large variations in the wind speed, even on the order of fractions of a second. Is that important? It can be. It depends on what you're going to be doing with this weather information. For example, at a meteorological research station, where there's some field deployed weather stations where we're trying to learn about things like how the surface of the earth is interacting with the atmosphere, things like the rate of evaporation of water off the surface, or the rate of conduction of heat out of the ground into the atmosphere during the day, and so on. Well, actually the very, very high frequency variability within the winds on the order of tenths of a second are actually what are determining things like the evaporation rate. Well, they're a very large factor in determining the evaporation rate and the rate of conduction of heat and so on. So at something like a meteorological field station, they would actually be recording the winds literally every 1/10 of a second. That's really cool. We'll probably have to look at examples of data like that later in the semester, but here's the deal. Those little variations, over the course of a few seconds cancel each other out. Those little gusts of wind, those little variations of eddies and dust devils and so on going by have no consequence whatsoever to like say flight operations. Okay, meteorologists in general don't care about those kinds of things. Notice a vocabulary word here. We learned resolution in the past to mean like, can we tell the difference between a wind that is 9.0 meters per second and 9.1 meters per second? Here we're talking about the temporal resolution. Can we tell the difference between the wind now and the wind a tenth of a second from now, or the tenth of a second ago, or a half second ago? Well, it turns out those kinds of observations don't make any difference for like flight operations. Whether the plane can land or whether it has to circle the airport is not about a gust of wind that lasted 0.2 of a second. So from that kind of purpose, we don't really care about it. Same with such high temporal resolution observations have no consequence whatsoever for like synoptic meteorology and forecasting. The high temperature today at these locations has nothing to do with, you know, a gust of wind that was a tenth of a second long or something like that. And no wind turbines, for that matter, can respond to such high frequency variability in the wind. If the wind gusts slightly higher for a few tenths of a second, it isn't like you're going to be producing more power from your turbine. It takes on the order of, you know, minutes for the wind turbine to accelerate and so on. It's huge. It has a lot of inertia. So we don't really need like tenth of a second resolution, temporal resolution to our observations when we're talking about these kinds of applications. For this, what we really need is more like the average wind speed. What was the average wind speed over time? As it happens, the World Meteorological Organization, which is an entity run by the United Nations, has researched the heck out of this and knows what will work, and they recommend that for applications like aviation and forecasting and power generation and so on, the World Meteorological Organization recommends using the 10-minute average winds. Keep track of the winds maybe every tenth of a second or something like that, but then take the average over that period of like 10 minutes to determine what the mean wind or the average wind is doing, because it will be a better representation of what the large-scale flow is doing. So when we looked at this file that is part of your textbook and might be used for some of the problems that are coming up, when we said that the wind speed was 7.42 meters per second at 5 minutes after midnight, what that actually means in this case is that this is the average of the winds over the last 10 minutes, ending at 5 minutes after midnight. The wind speed's average was 7.42 meters per second. Now, during that 10-minute period, half of the time the wind would have been higher than that, half of the time the wind would have been lower than that, varying on the order of, you know, fractions of a second to maybe a few seconds. But your wind turbine does not respond to tiny little variations like that. So it was not important for your application to know about that high frequency variability. If you were studying the rate of sensible heat flux, that's conduction of heat out of the surface of the earth into your atmosphere at your location, then you might need that tenth of a second information. But for like understanding the power your windmill is producing, 10-minute observations will be fine. Now, in the case of like the routine weather observations that come from National Weather Service offices and airports and so on, they are generally the 10-minute observation like that. They're the average over 10 minutes, and they are typically transmitted to the world once an hour. So like if it is supposedly the observation associated with, let's just say 2 o'clock, then what it means is they recorded the observations from 1:50 until 2 o'clock and took the average over that 10-minute period, and that is what they're reporting as the winds at 2 o'clock. In general, the anemometer's observations for the other 50 minutes of the hour are not in any way transmitted or stored or anything like that. They keep the anemometer running because if something interesting happens, like a front passes through and the wind shifts direction at, you know, as the cold front comes through and now the wind's out of the north, or as a line of thunderstorms come through and now the wind is out of the east or something, then they'll transmit a special report at like 35 minutes after the hour or something. But under routine conditions, you only get the observations once an hour, and they're just the average of the 10 minutes before the observation was taken. Would it always have to be 10 minutes? Well, no, there are actually other applications for other uses where, like, for example, I've seen equipment that was transmitting the 2-minute average of the winds. Okay, so you would get the average over the last 2 minutes, and, well, if you really needed 10-minute winds, get 5 of those averages and just average them together, and that would be fine. So you could reconstruct a standard 10-minute observation from what they have. There are a few, I've even seen 1 minute average winds. It depends on what you're going to be doing with these things. But in general, the standard established by the World Meteorological Organization is the 10-minute winds. But no matter what, you would always know this because there's always going to be documentation. If you are working at some wind power site and there's equipment on site, it will always be documented somewhere in the books, in the manuals, in the documentation from the person who had the job before you, whatever. Oh, this data logger is recording the 10-minute average winds, which is what we need for our model that is predicting the power output of this turbine. Okay, or it'll say someplace that, oh, these are 1 minute average winds, and then we just take the average of 10 of those 1 minute averages to get the 10-minute average. What you need and what the sensors in the data logger are giving you will always be documented. Okay, that in and of itself is not a tricky thing, it's just a job. All right, let's see if we can kind of take what we learned here and answer a few questions before we're done with this rather raspy lecture here. Question 1. At this hour, the National Weather Service office in Evansville, Indiana, where I live, is reporting that the winds are out of the south at 8.0 meters per second. We know that this really means blank 8.0 meters per second. A, at exactly the strike at the top of this hour, the anemometer said that the wind speed was 8.0 meters per second. B, average over the last hour, the wind speed was 8.0 meters per second. C, average over the last 10 minutes, the wind speed was 8.0 meters per second. Or D, the National Weather Service is forecasting that the winds this hour will be 8.0 meters per second. What does it mean that we've gotten this measurement that the winds at this hour are 8.0 meters per second? Make a choice from those 4 options and get a little feedback before we move on to question 2.